Everyone, so we are starting on page 5 in the notes, and we're going to be continuing with a little bit more factoring and also why we need factoring to be able to find some of our more complicated roots. So let's go ahead and take a look at number 5. We've got 9x squared minus 12x equals 45. What do I need to do first before I start factoring?
Find the GCF.
Even before that. For solving, it has to be in standard form first. So for factoring, first thing we check for is the GCF. For solving, we got to make sure our equation's in standard form first. So minus that 45. And now we're going to handle that GCF. What's the biggest thing I can take out of all of those? 3. So 3 is our GCF. That leaves us with 3x squared minus 4x minus 15 equals 0. Now, from here, we're stuck with that a value, which means we're going to have to do the x method to factor this. So I'm looking for a product of the first term, so 1x and 3x. Product of 15, let's see, 5 and 3, bless you. I'm going to go ahead and put the 5 on the bottom and the 3 on the top, and that's going to give me 5x. And 9x. Who do I want to be negative? The 9. So negative 9x plus 5x is negative 4.
I forgot my last period.
Go ahead and get it. So we need our 3 to be negative in order to get the 9 to be negative. So your last step before writing the factors is to make sure that we are getting the right product number. So is negative 3 times 5 negative 15? Sure is. So we are now ready to write the factored form. So 1x gets paired with the minus 3. 3x gets paired with the 5. Don't forget that GCF. So 3 times x minus 3 and 3x plus 5 equals 0. So now from here, I have 3 times something equals 0. So either this factor is going to be equal to 0, or this factor is going to be equal to 0. Hey, can 3 be equal to 0? Yes, no, yes, I'm not sure, Mrs. Cairo. So we are multiplying these 3 things together, but the only reason we're setting these 2 equal to 0 is because of the variable. They have the potential to be equal to 0. 3 is just the number 3. That is not going to give me an x-intercept, so it's only the variable factors we set equal to 0. So 3x equals negative 5. X equals 3. 3. Yuck. Not much space on this problem. And x is negative 5/3, and x is positive 3. Now, would we be able to see those roots on the graph? Would those show up as x-intercepts? Yes. So if I were to type in that equation, 9x squared minus 12x minus 45, we should see a root at negative 1 2/3, that's what negative 5/3 is, and another at 3. So I can see the roots, though solving by graphing, I wouldn't be able to find that negative 5/3 exactly. I'd just be like, well, it's somewhere between negative 1 and negative 2. So factoring is good for finding non-integer roots. So if I were to describe these using what we did yesterday, we would say that this has 2 rational roots. 2 rational roots. Now, folks, let's go ahead and take a look at this next one. 4x squared plus 2x equals 5. In order to solve by factoring, we would have to first put it in standard form. So 4x squared plus 2x minus 5 equals 0. Now I want to just go ahead and take a peek at the graph on this one. 4x squared plus 2x minus 5. And if we look at this graph, Does it look like factoring is going to help us? If you're like, it kind of looks like we have a root at 1. If I type in 1, we see that my graph isn't exactly hitting there. So it looks like we're going to have decimal roots, but we don't know if these are rational roots, like nice terminating decimals, or if they will be irrational roots or decimals that don't repeat or terminate. So let's see what happens when we try to factor this one. For 4x squared, we'll try 2x and 2x. Factors of 5, there's only 2, 1 and 5. 2x times 5 is 10x. 2x times 1 is 2x. Is there a combo of those, positive or negative, that will give me that sum number of 2x that we want? That's a no. Now, there's nothing else more to try for the factors of 5, but I can try 4x and 1x, a different pair of factors for the 4x squared. So 4x times 5 is 20x. 1x times 1 is 1x. How about that? Any way we're going to get to 2x as a sum? Nope. So that's out, and those are out. Last chance. 1x and 4x, that gives me 5x, and that gives me 4x. So, wah, wah. What do we say about factoring this?
Prime.
Can't be done. It is prime. So what this tells me is that these roots that I see on my calculator, are those going to be nice fractions or nice friendly decimals like 0.5? No, this is the same situation we had over here where I can see the roots, but since I can't find them by factoring, that proves that they are irrational. So I can find nice fractions and decimals using factoring, but if I can't find them by factoring and I can see them, that means they are irrational. So I want you to write 2 irrational roots. And we can show our little sketch on the calculator that it looks something like this. We can see them, but they are not friendly. We're going to skip number 7, and we're going to use this space over here to try number 8. Number 8, it is in standard form, but what value is it missing, A, B, or C? The B value. There's no x with it, so we've got x squared plus 4. Can I factor that as x plus 2 times x plus 2? Or x plus 2 and x minus 2? Is there any way for me to get a product of 4 and a sum of 0? I can do 2 and 2, 1 and 4, negative 1 and negative 4, or negative 2 and negative 2. Will any of those give me a sum of 0? That is a no. So this one is prime. Now, before we say it must have irrational roots, we're going to go ahead and take a look at this graph. X squared plus 4. Pew. How many x-intercepts does that graph have?
0.
None at all. So sometimes prime expressions are indicative of irrational roots, but other times, if the graph's not hitting the x-axis at all, prime means there are no real solutions. Oops, sorry, not 2. No real solutions, not 2. Now, why am I underlining that word real? Because though this graph doesn't have any real solutions, it does have complex or 2 imaginary roots. So what this means is I'm going to be able to solve this algebraically, but I'm not going to get something that's true. Or something that shows up on the graph. Folks, I want you to try the last problem on your own. I want you to type it in on the calculator and look at the graph and decide if we're going to be able to factor it. We go to type in the equation, x squared plus 4x plus 6. Are we going to be able to factor that? No. So what's nice about looking at the graph and why we did start with graphing, even though it's not usually the most efficient way of solving, is it does give us a preview of whether we're going to have solutions and what type they will be. So this graph does not hit the x-axis at all. So it has no real solutions, but it will have two imaginary ones. And we would say that that expression is prime. And it's true. Try to factor that. Product of 6, sum of 2, not happening. So you can use the graph and the factoring together to figure out what type of quadratic solutions you are going to have. So folks, any questions on those ones? I think we'll go ahead and wait on these for right now, and I'm going to turn you loose on some factoring with the homework quiz. Before I pass out the homework quiz, though, I'm going to explain the monster relay.